All right, let's jump right in. We're going to do a deep dive on Miras, but not just as a paper review. Think of this as an architectural breakdown. We're going to look at it from an engineer's perspective and figure out what we can actually build with this thing for our next-gen sequence models. Okay, so let's get straight to the engineering problem, the one we've all been banging our heads against. It's the transformer architecture, right? That quadratic complexity with attention, it's a killer. As soon as your context gets long, your compute and memory just explode. And that KV cache, it just keeps growing, eating up all your VRAM. Trying to deploy a long context model at scale becomes an absolute nightmare. And then you've got the other side of the coin, the modern linear RNNs. Yeah, they're fast. Linear complexity is awesome for scaling, no doubt. But, and this is a big but, they make a really tough trade-off. Their memory systems are, well, too simple. It's like they just keep piling new information on top of the old, with no real management. The memory just overflows, and they completely forget important stuff from way back. So you're stuck in that classic dilemma. Do you want performance, or do you want efficiency? We need to break out of that. All right, Section 1, the long context bottleneck. Let's really dig into what's going wrong with the current models out there. So if you look at what we've got right now, transformers, it's all about that massive KV cache. It's a memory hog, plain and simple. Then you have those early linear RNNs, the ones that just piled on new info, which led to that memory overflow we talked about. Delta rule models got a little better, but they still plateaued pretty hard. And even the fancy deep memory modules like Titans felt kind of patched together, right? There was no single coherent idea behind any of it. Okay, so now let's get to the good stuff. Miras, a new blueprint for sequence models. This is where the paper proposes a fundamental shift in thinking. Instead of arguing about attention versus recurrence, Miras says, hey, let's reframe the whole thing. It looks at all these models and says, under the hood, every single one of these is just an associative memory module trying to map keys to values. That's the core architectural insight. And this brings us to a really crucial concept, attentional bias. Now, from a coder's perspective, just think of this as an internal loss function. It's a mini optimization problem that the memory is constantly solving at test time, not just during training. It's deciding, on the fly, what's important right now, what do I keep, what do I forget? It's a pretty powerful idea. Now, check this out. This is where it gets really interesting. When you use this framework to map out the existing models, look at this table. See that attentional bias column? It's kind of shocking, right? RetNet, Transformer, Mamba, pretty much all of them are just using a basic dot product or an L2 objective. It's like we've been building all these incredibly different-looking models using the exact same 2 or 3 Lego bricks. There's almost no variety in the core memory function. So what Miras gives us is a toolkit, 4 distinct levers we can pull when we're designing a new model. First, the memory structure. You can pick a vector, a matrix, maybe a whole MLP. Second, the attentional bias. That's your internal loss function. Third, the retention gate, how you're going to regularize things. And fourth, the memory algorithm, how you're actually going to update the memory, like with GD or momentum. Suddenly, designing an architecture feels less like black magic and more like, actual engineering. All right, next up, novel building blocks. Now that we have these levers, let's see what cool new components we can actually build with them. So let's pull that attentional bias lever. You know how standard L2 loss can totally freak out over a single outlier? One weird token comes in and throws your whole memory out of whack. Well, what if we just swapped it out? Put in a Huber loss instead. Now, as you can see here, it acts like a smart switch. For small errors, it's just L2. But for big, surprising events, it flips over to L1, effectively capping the influence of that outlier. You're literally engineering robustness right into the memory cell. And it's not just the bias. We can get way more creative with our retention gates. Instead of just a lazy L2 decay, why not use KL divergence? I mean, think about it. It forces your memory weights to act like a probability distribution. They have to sum to 1. That's a brilliant built-in way to stop them from exploding. Your update rule just becomes a softmax. Or what about elastic net? You get this nice mix of both scaling things down and just zeroing out unimportant stuff. It gives us way more precise control over memory. So to prove this whole framework isn't just theory, the paper actually builds 3 brand new attention-free models. You've got Moneda, Yod, and Memora, and each one is just a different combination of the levers we've been talking about. Moneda plays with L-pi bias and LQ stability. Yod, that's the one that uses the robust Huber loss we just looked at. And Memora sticks with an L2 bias, but pairs it with that cool KL divergence gate. Okay, Section 4, Performance and Trade-offs, the verdict.
The architecture is cool for sure, but does it actually work? And maybe more importantly for us, what's the catch? What's this going to cost us in terms of complexity and resources?
First up, language modeling perplexity. You can see the numbers here. Lower is better. And yeah, the Miras model, YOD, comes out on top. At the 1.3B scale, it's beating out both Mamba 2 and gated DeltaNet. So right off the bat, we know this isn't just some academic exercise. This blueprint can build models that are seriously competitive.
But this is where things get really impressive. Check out the needle in a haystack recall. This is the ultimate test of long-term memory. At an 8K context, Mamba 2 has basically forgotten everything. Its accuracy craters down to 31%. But Monida, one of the Miras models, is sitting at a near-perfect 98.8%. That's just a night and day difference. It's a direct result of having a better memory system. It actually finds the needle.
Okay, but let's be real. This kind of performance never comes for free. Here are the trade-offs we need to be thinking about. First, if you use an MLP for your memory, your parameter count and VRAM usage are going to go up. No way around that. Second, you can't just drop this into an existing codebase. The parallelization is different, it needs a specific chunking logic, which means more implementation work. Third, if you're using these fancy new biases, you've got to be careful about gradient stability. You'll need to implement smooth approximations for things that aren't differentiable, and that's a classic place for bugs to hide. And finally, yeah, you've got more knobs to turn. Finding the right hyperparameters here is going to take some serious work.
So here's the bottom line. Miras isn't just one more model to add to the pile. It's a blueprint. It's a whole design space. For us as engineers, it's a toolkit that lets us stop grabbing off-the-shelf backbones and start actually architecting solutions tailored for our specific problems. So the real question it leaves us with is, what are you going to build with it? What custom attentional bias does your problem need?